have Lothar here. You can see the title. And I think that's all right. So you can see.
Yeah. 1 second before I start. I think I made it a bit. Yeah, you see, a bit too big. So, okay. Thank you very much for the invitation. For allowing me to give a talk. So, maybe I start with some apologies. So the first one is I apologize for slides. I don't like it when people give slide talks, but I do it all the same. And the reason is that I give so many, that there are many formulas. So that's the second excuse. And the third excuse is that I really don't know what higher structures are. And so you won't see any. So I apologize for that. Anyway, so but there is some geometry and something. Okay. So we are talking about Vafa-Witten invariants. So let me start. So if X is a smooth projective surface over the complex numbers, whose first Betti number is 0, and the geometric genus should be positive. So we have a form. Then we want to study invariants of domain property. Then we want to study the invariants of modular space based on that. So we have here this modular space M. And so the simplest invariant one could consider is the Euler number. So we could look at the generating function, which is just the sum of the Euler numbers counted with q to the n, where n is the second Chern class when we fix the first. And one example of this is this old formula that if we look at the modular space of rank 1 sheaves with second Chern class n, this is just the Hilbert scheme of n points on S, which parameterizes either zero-dimensional subschemes of length n, or if we want to view it as a rank 1 sheaf, rather their ideal sheaves. And in that case, if we the Euler number, the generating function for the Euler numbers as above is up to this trivial shift, just the eta function to the power minus the Euler number of the surface, where this eta function is the 24th root of the discriminant function and is a modular form of weight 1/2. And so very roughly speaking, in 1994, Vafa and Witten had this paper, A Strong Test of S-Duality, where they say something different, but if one wants to say it very naively, one could say the Euler numbers of the modular space of sheaves, the generating function for these Euler numbers should be modular forms. We'll see what the more precise, but I think maybe more than this. This one has the, let me go back. Yeah, but the story is more interesting anyway. So it doesn't matter here, but it matters later when something is actually missing. Okay, so now these moduli spaces are in general singular, but and in particular, it's maybe not very likely that the Euler numbers will be particularly nice, but they are what one could call virtually smooth. In fact, what this means is, so if we have a moduli space, then at every point in the moduli space, we have a tangent space, which is the space of first order deformations of the objects of the model that are parameterized by the moduli space. And we have an obstruction space, which is the space in which the obstruction to extending deformations to higher order live. And so there's a notion of perfect obstruction theory, which means we have a complex of two vector bundles on the moduli space, which are globally defined, such that at every point in the moduli space, so for every object in the moduli space, the kernel of this map is the tangent space, and the co-kernel is the obstruction space. So that means we have two vector bundles on the moduli space with a map between them, which captures everything about tangents and obstructions. And in that case, we call the virtual tangent space the formal difference between the tangent space 0 and D1. And the virtual dimension will be the difference of the ranks. And if M is compact, then by some big theorem by Bernd van Tecke and Li-Tian, we get a virtual fundamental class on the moduli space, which lies either in the Chow group corresponding to the virtual dimension of the moduli space or in the corresponding homology group. And it somehow behaves as if it was the fundamental class of a smooth space. So our moduli space of rank R sheaves on the surface has such a perfect obstruction theory of virtual dimension. This number 2RC2 minus R minus 1 C1 squared minus R squared minus 1, the holomorphic Euler characteristic of the surface. In fact, the tangent space will be the trace-free X1 from the sheaf to itself, and the obstruction space, the trace-free X2, and by Riemann-Roch one gets this dimension. And in this situation, we can define the virtual Euler number, which is just, we virtually, we just kind of formally use the Hodge index theorem, which says that the Euler number is the integration of the top Chern class over the space. And so we do this all virtually. Okay, so this is the situation. And now I want to come to the Vafa-Witten invariants. So they were introduced in 1994 by Vafa and Witten, more generally for four manifolds using the physics language. In algebraic geometry for algebraic surfaces, they were, a mathematical definition was given by Tanaga and Thomas in 2019 using a moduli space of Higgs pairs, and I briefly call that. So we have a projective surface with an ample divisor. So a Higgs pair on S will be a pair of a sheaf, a torsion-free sheaf on the surface, and a homomorphism from the sheaf to the sheaf tensor Ks, so an endomorphism, twisted endomorphism of the sheaf, whose trace is 0. And there is a notion of stability, which is somehow the usual one. Essentially, it says that the kernel should be stable, and we have a moduli space of rank R stable Higgs pairs. So this moduli space again can be very singular, but it admits also an obstruction theory, which now is even symmetric, which means that we have this, this pair of vector bundles, which can have just the obstruction theory, but now E1 is the dual vector bundle to E0. In particular, this implies that, and this follows rather obvious definition, and in particular, it follows that the virtual dimension of the moduli space is 0. So now, in principle, then we should be immediately able to compute the Euler number or the virtual number of points, because we just want to integrate. Our Vafa-Witten invariant would now be the integration over the virtual fundamental class of 1, because it's 0-dimensional, so it's the virtual number of points of this moduli space. So the moduli space obviously is not 0-dimensional, but virtually it's 0-dimensional. Its fundamental class has dimension 0. There's a problem with this definition. This moduli space is not compact. And that's kind of obvious from what I write below, because we can rescale the Higgs field. We can multiply it by any element in C star. And obviously that means we have a kind of vector bundle structure of this thing, and it certainly cannot be compact. But on the other hand, the solution is also the same. We have a C star action, namely again by rescaling this Higgs field, and the fixed locus is compact. And so then we could just say, if the space was compact, then and smooth, one could use the Bott residue formula to compute things. And if it is compact and is virtually smooth, one can use the virtual version of the Bott residue formula if it was compact. But okay, it's not compact, but we still use the virtual version of the Bott residue formula and take this as a definition. So we take the Vafa-Witten invariance will be the integral over this. So what one would view as the integral of 1 over the virtual fundamental class of this moduli space is just defined via what residue formula or what Atiyah-Bott localization as the sum over the integral over the fixed point locus with its virtual fundamental class. It inherits one over the equivalent Euler class of the virtual normal bundle of the fixed point locus. So the virtual normal bundle will be what one calls the moving part of the virtual tangent bundle. So that just means the part on which the action of C star is non-trivial. So the sum of the eigenspaces where the eigenvalue is non-zero. And this thing will decompose into components corresponding to the components so this number, the Vafa-Witten invariant, will be a sum over contributions, one for every fixed point component. And we have indeed such components or units of components which are parameterized by partitions of the rank R that we are considering. Namely, we have the component corresponding to a partition lambda parameterizes the situation where our parameterized sheaf decomposes as a direct sum of lower rank sheaves, and the Higgs field phi sends always one of these EI to the next, goes from one to the next, then it's OKS, and the last one is 0. And the lambda then, which is the partition which is given by the ranks of these AIs. Okay, so I just put this there again so that you remember for a moment. And so there are in particular two special components. One is the so-called horizontal component, where this partition just consists of one piece, R. And so this means we have a sheaf, we have a Higgs field which is 0. So that just means, and the stability says the kernel should be stable. So that means this, this component is just the moduli space of rank R H-stable sheaves. You can also see that, you know, the moduli space is virtually zero-dimensional, but one of the fixed point components is the whole moduli space of stable sheaves. So it's kind of a little bit strange. And in this case, in fact, Tanaka and Thomas show that the virtual Euler number that I mentioned before is just equal to the corresponding part of the Vafa-Witten invariance. So thus the Vafa-Witten invariant contains the virtual Euler numbers of the moduli spaces of sheaves. Okay. And we have on the other side, most extreme side, we have the vertical component, which is when the partition is just 1, 1, 1, 1, 1. That means the sheaf splits into rank 1 sheaves. So basically, ideal sheaves tensorized by line bundles, and then the map always sends one to the next. The last one is sent to 0. And so that somehow should be related to Hilbert's scheme of points. And Tanaka Thomas shows that it's a little bit better than what I said before, namely the invariants are not parameterized by partitions, but just by divisors of the rank R, namely the virtual fundamental class of a component corresponding to lambda is 0, unless all the parts of the partition are equal. And so in particular, if the rank is a prime number, we have only two parts, the horizontal part and the vertical. Okay. So now we can combine this whole thing into what's called the Vafa-Witten partition function. We actually have a, yeah. So basically you can see we just count again for the Vafa-Witten invariance with the virtual dimension of the Q to the virtual dimension of the moduli space of sheaves, same invariance, and then we have some trivial prefactors, and we for some reason divide by 2R. Okay, I mean we or whoever wrote this down the first time. Okay, and it's written like this because we want in the end to have some modular forms. So now again, according to what we said, this doesn't really work so well. So this will decompose with contributions corresponding to partitions lambda, or rather to divisors of R, where the lambda is will be the contribution of the corresponding component of the modular species. And now S-duality predicts a certain behavior of this generating function under modular transformations. And this is the following conjecture of, well, maybe I should. So if now this Q, which for some reason I've always written as Q, if I view that as e to the 2 pi I tau, where tau is a point in the complex upper half plane, then I can consider what happens if I replace tau by -1 over tau. We want to have some kind of modular property. So the non-trivial element in the SL2Z for considering modular forms is the S transformation, which sends tau -1 over tau. And in that case, we get this transformation behavior that it transformed. You have some transformation like a modular form of weight, Euler number of the surface divided by 2, some trivial p factor. And then we see that the invariant for C1 corresponds to the sum over all the invariants for all the first Chern classes modulo R times the second cohomology, with however weighted by powers of a root of unity like this. So for one, so we have this kind of transformation, which is very strange. It kind of involves all these different invariants in one function, and it is not very clear why anything like that could possibly be true. Anyway, so this is one of the predictions of Vafa-Witten. So in particular, it's not obvious from this, but this will interchange the contribution of the vertical and the horizontal Vafa-Witten invariants. And so in particular, if the rank is prime, we believe in this conjecture, we only need the vertical Vafa-Witten invariant to know the whole Vafa-Witten. Okay. Okay. So now I want to start, how one could possibly try to compute something like that. So one of the things is that we have what one could call universality, universal formulas for these Vafa-Witten. So let's look at this for the vertical partition function, where one can actually prove it. So we have this vertical partition function. We can express it in terms of some universal power series. First, we have again our friend the eta function and its 24th power, which is the discriminant function, the most well-known modular form. And we consider this version of delta A. This was not what I wanted, but anyway. We consider this delta IB. So we say it's 1 if A and B are congruent, are equal to either modulo the R times the second cohomology, 0 otherwise. And then we have this crazy formula. So there are some universal power series parameterized basically by pairs of numbers smaller than R-1. We have also this, which are power series, Laurent series in Q to the 1 over 2R, such that now for all surfaces and all first Chern classes at the same time, this Vafa-Witten generating function, the horizontal, the vertical part, is given by products of sums of products of power of these universal power series. First, we have this delta function in the denominator to the power of the holomorphic Euler characteristic. Then we have this first unknown power series for ks squared, the canonical class squared. And then we sum, maybe I put this right there so you can see it. Uppsala, that was too fast. Then we sum over all classes beta. I mean, tuples beta of classes in the R-1 classes in the second cohomology. We only count it if C1 is equal to some I times d beta I. Then we have the product of the Vafa-Witten invariants of these classes, and we take the product of theseCij's to the beta I times beta j. So this Vafa-Witten invariants are certain C infinity invariants of four manifolds, which are quite well known. They are maybe rather subtle in the context of four manifolds, but for algebraic surfaces with PG bigger than 0, they are very easy to compute. So the most simple case is if we have an algebraic surface with PG bigger than 0 such that the canonical linear system contains a smooth connected curve, then there are only two classes in the second cohomology for which the Vafa-Witten invariant is non-zero, and this is 0 and the canonical class. And in one case, the number is 1. In the other case, it's -1 to the k of s. All the other ones are 0. So in that case, you can see that this formula would simplify quite a lot. You can see it's a very complicated formula, but the thing is, it works for all surfaces and all C1, and for all ranks, you get the same kind of formula. And everything is in terms of these universal power series. If one wants to understand this series in some sense, the task is to determine what these universal power series are. Okay, and that's what we are kind of trying to do. Okay, we have a few, so I review this thing so that you remember at least for 2 minutes. And so, so there are a little bit fewer such power series than one thought. So for one thing, there's a symmetry relation, Cij is equal to Cr minus j, R minus I. And this was originally conjectured by me and Martijn, and then it has been proven by Arbuthnot, Bohl, and Ralaraga. And there are also blow-up formulas relating the invariance of the surface and its blow-up point when one changes the C1 by any multiple of the exceptional divisor. And these will relate these generating functions in terms of theta functions for the corresponding AR -1 lattice. Okay. So, okay. And now there is supposed to be this S-duality transformation which relates what happens for the vertical and the horizontal Vafa-Witten invariants. And so we, and one can also in addition do computations to compute these invariants up to a certain order. And so from this, we conjecture that in some sense, one has the same formula also for the vertical Vafa-Witten invariants. That means for the Euler numbers, the virtual Euler numbers of the moduli spaces. So only with some subtle differences, somehow dual. So we have here the same term delta, only q to the r becomes q to the 1 over r. Then we have the same kind of functions. We call them d instead of c. And we have again the Vafa-Witten invariance in the same way. The formula has the same structure, except that this delta here, so this summing over the delta, we instead sum over the product of these rth roots of unity to the corresponding power. Okay, so that's a little bit like some kind of Fourier transform. So, okay, and so this is a conjecture. Now, I've heard some talks by Joyce where he announced the proof of something similar, which might actually contain this as a special case, but I mean, I haven't seen an explicit enough version to be completely sure. Okay. So he has a much more general thing that everything of a certain kind one should be able to write it as in terms of universal product formulas involving the Vafa-Witten invariance. But yeah, it's supposed to be a few hundred pages of proof, and so one will have to wait for it to come out or what it precisely is. Okay, and so in addition, we claim that these generating functions for the vertical and horizontal Vafa-Witten invariants are related by modular transformations, by the most obvious one, namely by the S transformation. So we claim that again, if Q e to the 2 pi tau, then d0 of tau is C0 at -1 over tau, and dij of tau is equal to Cij -1 over tau. And in fact, it also says that, and so if we know these functions C0 and Cij, then we also know, for instance, the virtual Euler number of the moduli spaces. And if the rank is prime, then we know the whole Vafa-Witten generating function, if we believe in the conjectures of Vafa-Witten. Okay. So now I want to say just a few words about how one compute such a thing. So, and so I say it first for these vertical ones. So in this case, so this vertical moduli space parameterizes E phi, where E is a sum of rank 1 sheaves, and E is always given as a map from EI to EI minus 1 tensor Ks. The last map is 0. And so that means that EI is just the ideal sheaf of a zero-dimensional scheme of some length tensorized by a line bundle. And so that means, and one can precisely say which one will be there. And this means that this vertical generated function can be computed on products of Hilbert scheme of points as a certain intersection number there. And in fact, there is an old theorem with Ellingfield and Lane, which is a universality theorem for Hilbert schemes of points, which says that certain kinds of intersection numbers on Hilbert scheme of points are universal polynomials in the corresponding intersection numbers on S. So that means, okay, I can explain this better if you want, but, and so in particular, this is also used to prove Laraka's universality theorem. And then once one knows this, one can determine these universal power series, C0, Cij, by looking at enough examples. In particular, we can take as examples toric surfaces. So that's a surface which has a C star action with finitely many fixed points. And the action will lead to the Hilbert scheme of points. And the fixed points will be parameterized by tuples of partitions. So the idea is that, so the Hilbert scheme parameterizes these ideal sheaves. So then in the subschemes parameterized by the fixed points will be concentrated in the fixed points on the surface, and in local equivariant coordinates near the fixed points, the ideal of the subscheme will be generated by monomials. And the monomial I can write as x to the n1 to n0, y to the y times x to the n1, and so on, where these ni form a partition of a certain number. And so that's how it comes to pass. And then we have the Watt residue formula, or the Atiyah-Watt localization, which tells us that one can compute things in terms of local data near the fixed points. And it turns out that this can be expressed in terms of the combinatorics of the partitions. And so we can just do all this. So one can either be smart and understand what this formula is, or one can be stupid like we, and just put this all in the computer, and it will compute to many coefficients. And so that, and so the horizontal invariants are similar. There's a Mochizuki's formula, which expresses, again, invariants of modular spaces of sheaves on surfaces. So this modular space of rank R sheaves in terms of products of intersection numbers of Hilbert scheme of points. It's unfortunately a very complicated formula, but again, one can compute with this, these invariants. The only thing is that for the horizontal invariants, the formula is so complicated, particularly gets complicated very fast. When the rank grows, one cannot go very far. Okay. So now there's a tiny trick to this, which I consider, which is the twisted version. So I want to consider just a very tiny twist to it, which is now I consider moduli of L tensor Ks Higgs pair. So that just means we have our sheaf E together with the homomorphism from E to E tensor L tensor Ks, where L is a line bundle. It seems kind of a little bit stupid, but okay, it turns out to be kind of nice. So again, we have the same situation, and then we can we have such a virtual fundamental class, and we can define the twisted Vafa-Witten invariance by integrating 1 over the corresponding moduli space. And then we have again the vertical component and the horizontal component, the same proof as Laraka's proof of tiny modifications, will prove the corresponding universality formula, which is basically the same as we had for Laracher, only we have a few more universal power series. We have all the old universal power series which occur in the same way, but we have a few more. We have here something to the power L squared, something to the power LKS, and something to the power the Vafa-Witten class times L. And basically that's always the property with this universal formula. You take all the numbers you can naturally get on the surface out of your problem, then you do it in terms of that. And so, but one thing which is surprising here is that all the new power series we know. I mean, one can find out what they are. So this d is just 1 over the eta function of q to the r to the r squared. The b is just expressible in terms of the others. And for the for these BIs with the Vafa-Witten invariants, we have this explicit formula, which is maybe a little bit crazy, but anyway, so if we take the logarithmic derivative of this thing, it is the square root of this expression in some kind of Eisenstein series for some congruent subgroup, which looks like this. And so it's everything explicit. So we know these completely, the new power series. So, okay, so in some sense, that's not so so great. So we have introduced these new invariants, and we have shown that we can express them in terms of the old. There's, however, one more point which I did not mention. These new invariants can be expressed also as invariants of, so the, I didn't mention it, but instead of at Higgs pairs, you could also view the moduli space of Higgs pairs. You can also view it as a moduli space of sheaves on Calabi-Yau threefolds and on a local Calabi, which is the total space of the canonical bundle of the surface. And these invariants twisted by L, you can view as invariants on a Calabi-Yau fourfold, which is where one also involves this L. So in that sense, they are also new invariants from a geometric point of view. But there's one other thing, namely, there are also further relations. We also find that the CII are expressible in terms of the others. And so this means we actually get something for free. So, you know, R of our unknown power series, we suddenly know by just introducing new invariants. Okay, so we now only need to know the Cij with I smaller than j. Okay, and so, and this follows from some version of Serre duality. So, and so therefore, it turns out the vertical Vafa-Witten invariants will be determined by just knowing the Cij, where for I smaller than j and I plus j smaller equal to r. So using this, conjecturally, we determined until now the vertical and horizontal Vafa invariants for rank at most 13. Which is, and for r small equal to 5, there's an old paper with Pohl and Laracher where this was done by other methods. And so let me little bit talk about this. So this is in terms of modular forms. So look at congruence subgroups of PSL2Z. So we have gamma of R, which is the elements which are congruent to the identity matrix mod R, gamma 1R, where it's congruent to the matrix which the upper corner is 1, 1, and anything, and gamma 0R, where the lower left corner element is 0, modulo R. It's always modulo R. Okay, so these are certain subgroups. And so if we have such a congruent subgroup, we can look at the upper half plane, and the function f from the complex upper half plane to the complex numbers is a modular form on gamma if it is invariant under the action of the subgroup, where the action is by broken linear transformation. So the matrix ABCD acts by sending tau to A tau plus B divided by C tau plus B. It turns out to be an action. And in addition, we asked that f is meromorphic on the upper half plane, and it's also meromorphic at the cusps. So that means that, for one thing, this has a development in powers of q, q to the 1 over r, where there's only finitely many negative powers, and this is also true after transforming it with any element in SL2Z. And so modular functions actually turn out to be, if we look at the modular curve, which is h, the upper half plane, divided by this group, this will be a curve which parameterizes elliptic curves with certain properties. And the functions will actually be rational functions on this. And for instance, in simple cases, this curve will just be isomorphic to P1. Then the field of rational functions on this curve is generated by just one element. And so if we have such an element, then we call it a Hauptmodul. Usually we also assume that it will have a pole or zero at infinity, but anyway. So, okay, and so in particular, if we look at our congruent subgroups, we have, as I said, this will be modular space of elliptic curves with extra structure. So for gamma 1R, this is an elliptic curve with an element of precise order R. So such a thing will generate this cyclic subgroup of the elliptic curve, and then gamma 0R parameterizes instead the elliptic curve together with the cyclic subgroup of order R. So they are obviously related. And so, okay, so I wrote this there. So now let's rewrite M gamma for the field of modular functions on R. So for n, a number which is prime to R, we take an element an in the quotient gamma 0 by gamma 1, which sends EP to En. Then an acts in the same way on the indices. So the claim is, so this is the conjecture or the claim, that this element acts on our universal power series by acting on the indices of our universal power series Cij, so that these things are connected. So the modularity is in the way it kind of interchanges and acts nicely on our universal powers. So this is the conjecture which I checked, as far as I could compute. So we have that. So it's not precisely true when I say that Cij, so the first one is true, but anyway, let me just say it like this, although I'm lying ever so slightly. So this, if in the case we have I and R minus I, so I plus Cij with I plus j is equal to R, then this thing itself will be a modular form on gamma 1R. And as I said, this element an will act by sending I to In and R minus I to R minus I times n, where I mean this by saying that I consider the indices modulo R and I consider Cji to be Cij. Okay. And with this, the action is just like this. So they are commuted by this action in this way. And for the elements Cij, which are where I plus j is not equal to R, it doesn't turn out to be true that they themselves are modular forms on gamma 1R. But if I consider Cij and Cir minus j together, then they satisfy, Cr minus j to the minus 1 together, then they satisfy such a quadratic equation where the coefficients are modular forms or modular functions on gamma 1R. And again, the action of this element an, moving the points to n times the points, acts in the indices in the same way. And so, so in some sense, so that means, so if we knew which modular forms there are, either as these Cij or as the coefficients of these quadratic equations, we would know all the Cij and we would know the whole vertical Vafa-Witten invariance. And therefore, in the case when R is prime, and if we believe in the Vafa-Witten conjecture, we would know the whole Vafa-Witten partition functions, also the virtual Euler numbers of the moduli spaces. So in the case So for r smaller equal to 13, we explicitly computed and checked up to q to the 13 that it is correct that theseCij's, so what precisely theseCij's are. So we give them explicitly as modular forms. Okay, and so let me give some examples. So I think I will be most likely a bit too fast, but that's maybe not the end of the world. Okay, so let's first look at the case I equal to 5. So this is so there's this famous Roger-Ramanujan continued fraction, which is this r, which here I have not written as a continued fraction, but rather just as an infinite product. So a very nice product formula. So product 1 minus q to the 5n minus 1, 1 minus q to the 5n minus 4 with a similar denominator. And this thing, if I take the 5/5 power of it, it is a Hauptmodul for gamma 1, 5. So that means it generates the modular functions on 5, and as rational. So every modular function on gamma 1, 5 is a rational function in this R. And this, if we take this as a generator of this A as a generator of gamma 0, 5 modulo gamma 1, 5, then it acts on R by sending R to -1 over R. Okay, so this is a simple thing. And then we compute up to q equals 13. We find that the vertical invariants are given by this explicit formula in terms of R. So we have a very simple, we have these simple rational functions. So here the C4 is given by this simple quotient. You can also see that what I meant by lying about it being a modular form for gamma 1r, there is this kind of trivial prefactor, the r in the denominator. It should be something in r to the 5 to be on gamma 1. But apart from that, it's true. And so then, and the other ones are given by applying this. And we have these quadratic relations where we explicitly know these the coefficients of the quadratic relation for the other ones. And this determines all the Cij because there are not so many in rank 5. And so therefore this tells us what all the invariants are in rank 5. And the Dij, one applies -1 over tau to it, and it turns out that this corresponds to replacing R by 1 minus phi R by phi plus RQ, where phi is the how to call it, the what?
Golden ratio.
The golden ratio, yes. Okay, so that's this I equal 5 case, so it's kind of rather cute. Also, that one gets this nice continued fraction. I mean, we don't see the, but I mean this famous function. And so in the case of rank 7, it's in some sense also quite interesting. So we look at these 3 functions, x, y, and z, which are again given by some nice infinite product like this, always looking similar as before, some q to the 7n, 7n minus 1, 7n 6 minus 6. So these are now modular cusp forms of weight 2. So they are modular forms, not modular functions, to satisfy this relation. You compute that this is 0. So that means, so this is the famous Klein quartic, which is a genus 3 curve with the maximal number of automorphisms, 168. And this is now realized as a modular curve like this. So, so we can take the, so here I wrote it wrong, but anyway, S and T, if I take the quotient of the coordinates, these are modular functions, not modular forms on gamma 0. And this thing is a Hauptmodul, so it generates things as rational functions. So the rational functions on these curves are given by expressions in this. And then we also have this, which is a corresponding thing for gamma 0. And then in terms of this, we can write, we can also see that this element which generates the quotient of gamma 0 divided by gamma 1 is acting by sending x to y and y to z. So we have a nice cyclic permutation of the coordinates. And so if we do this, we get that the invariants are given by this formula. And first, when I plus j is 7, we get this thing. It looks kind of complicated, but it could be arbitrarily more complicated. And then we have this. Okay, so one maybe cannot see very much. So the only thing which is maybe slightly, so the thing which is kind of interesting is that the denominators, that there are some repetitions. One doesn't see it so much here, but one sees it, for instance, this part of the denominator is the same part, this denominator, that's not obvious at all. So the different universal power series are somehow related in an interesting way. And, you know, everything is explicit. Okay. So now, and so just so I mean, that's not really the point. I don't really use that this thing is modular 4 for gamma 0 for gamma 7, but here one can see, in some sense, the modular curve for gamma 7, which is, so one can view the upper half plane as the disk, you know, within another model. In this case, we have this tessellation by pentagons, and in terms of this pentagon, you can take the fundamental domain for gamma 0, for gamma 7, and if we identify the edges with the same color or the same number, if you have very good eyes, then you get actually the corresponding curve. So one has a very pretty picture for this, which is of encoding the geometry. But I'm not using this in any way, but at least I want to have at least one picture, even if it's only vaguely related. So now let's look at higher rank. So for higher rank, the thing is, I mean, the difficulty was, you know, we want to express everything in terms of modular functions that we know. And so one has to know enough modular functions which are easy to handle. And so I kind of needed to find a way to get nice modular functions. And so the thing that I've found in the literature are the so-called Siegel functions, which are modular functions which have a nice expression in terms of as infinite products. So which means that they are, so we have an infinite product which in terms of Q, which means which in particular also means they are holomorphic without zeros on the whole upper half planes. The zeros and folds only occur at the cusps. And so in that sense, they are what is called modular units. Anyway, and so the one, we use only part of the Siegel functions, but here I have written down the formula for them. So we have this, which looks very similar to, in some sense, what we saw before, namely, so we have some trivial prefactor, which is necessary to make modular. And then basically we sum over, we take the product over Q to the Rn plus I times Q to the Rn minus I for a certain fixed I. And this is the thing for R, okay? So a very simple thing. It's also, you know, if you know, theta constants, get theta constant if you add some eta function here. So it's very similar to that also. Anyway, so if it's not completely obvious, but you find that Gi is equal to Gr minus I and Gr plus I is equal to minus Gi. If you work it out, you can see that. And these are not by themselves quite modular functions, but you can combine them in nice ways to get modular functions. So if you mostly by considering products of them. So for instance, if the sum of the ni's is 0, and when I make this product, now all the we only have powers of Q, so all these rational powers kind of vanish, then we get a modular function on gamma 1R. So in this way, we can get the modular function. And so without noticing, we already used that before, namely our R has such nice product development. It's just, and it turns out it's just G1 divided by G2. And the functions that we had in rank 7 now are, this H, S, and T are also just simple monomials in these Siegel functions. Okay, and so one can, to some extent, reformulate this kind of structural conjecture that I had before in terms of the Siegel functions. Namely, if I take Ci r minus I, it's a rational function in Siegel functions with the same r, obviously. And to get from, if I instead replace I by In, r minus In, then this is obtained by just doing the same to the indices of the Siegel function. Okay. I think this can be reinterpreted as saying that we have the Y representation of anyway. And again, we consider the indices with the same weight as before. And the same is true for if we take, we have this quadratic relation, ij and ir minus g to the minus 1, where the coefficients are now, again, rational functions in the Siegel functions. And when we move the indices of the ij, then we do the same to the Siegel functions. Okay, so this is how, so to speak, this operation acts on that. And I can make this explicit until r equals 13. So that means we know all the Cij until then. And thus we also know explicitly the Eij, because after all, I told you that these are, these have nice modular behavior, even though they're not quite modular forms, but one can precisely say how they act under the modular group. So we know if we apply -1 over tau to it, what happens. And so we can write down also, when we know the Cij, we can write down the Dij explicitly. And so we know, at least when we believe in my conjecture, and we certainly know until certain order that what the Euler numbers of the virtual Euler numbers of the modular space of sheaves on surfaces are in rank up to 13. So now, how does one go about finding this? So one of the problems is that, there are very many Siegel functions. You have and so there will be extremely many polynomials in them. It wouldn't make much sense to just try to write down a general formula in terms of the Siegel functions. So we need to express these things in terms of fewer functions. So if r is smaller than or equal to 10 or equal to 12, then the genus of the modular curve h modulo gamma 1r is 0. So we can find a Hauptmodul, so a generator of the modular functions as rational function, so that every function is a rational function in it. And then we have to find only this rational function. And we will find such a generator always as a Laurent monomial in Siegel functions. In fact, a Laurent monomial of degree 0. So we have a monomial certain degree in the numerator, monomial of the same degree in the denominator, and this will then automatically be an element in gamma 1r. And we find the Hauptmodul in this form, and we express the Cij in terms of this. And this is, in some sense, what we did in the rank 5 and rank 7 case, only that we didn't know we were working with Siegel functions. And now it's more complicated if one goes beyond. So h modulo gamma 1 11 has genus 1, and h modulo gamma 1 13 even has genus 2. So we don't have a Hauptmodul in that case, because it's not the rational functions on this thing is just not just rational functions in one variable. So it's a bit more subtle. And so we want to, just to illustrate, we want to look at the most complicated case, which is the case of rank 13, where it also seems to work. Kind of, there's a nice symmetry also there. So this is a curve of genus. So h modulo gamma 13 is a curve of genus 0. So, thus, it is hyperelliptic. So that means it has a unique double cover, a unique way double cover of P1. So we can consider this double cover. And we want to find coordinates, obviously as modular functions on h modulo gamma 113, which are compatible with this structure. So we want to find coordinates which, for some reason, we have x1, which is equal to x5, x2 equal to x3, x4 equal to x6. So there are only 3 coordinates, but we number them 1 to 6. And we also have coordinates y1 to y6 on this thing. So such that the xi's are pullbacks from P1, and and in pairs the yi are coordinates kind of which correspond to the fiber, which are interchanged by the hyperelliptic involution. So y1 and y5 is interchanged, y2 and y3, y4 and y6. So we want to find this in terms of our Siegel functions, obviously, because that's the only thing we have. And so what we find is we define our x1 to x6, y1 to y6 in this way. Xi is equal to gi divided by g5 times g5, as you can see, and the yi are in this form. And you can see, for instance, immediately, you can see immediately that this thing is actually, if I replace I by 5i, then I get the same thing. Because if I place this I by 5i, it's 5i. If I replace this by 5i, I get obviously 25i. 25 modulo 13 is -1, and -1 gives me the same as +1, because we know that gi is equal to g minus I. And so, and the same is true for the denominator. So we get this, and so we have this way of writing all these things. And so, and then we find that we have this nice quadratic. So the yi, so if I fix I, the yi and y5i in each case satisfy this relatively simple quadratic equation with coefficients the corresponding xi. So this determines, this shows that it's which kind of establishes my curve as a double cover of P1. This is the equation of the double cover. Okay, so we have the geometry, this hyperelliptic thing, we have now encoded in modular functions, and everything in terms of the Siegel things. And so then in terms of this, now I just throw it to the formulas. We have these nice polynomials. So I mean, I maybe should say, let me go back. So we have this quadratic equation. So this tells me that if I have any polynomial in xi and yi, I can get rid of all the powers of yi except for the power 1. Because if I have a quadratic term, I can replace it by something in terms of the xi. So therefore, I can expect to get, if I have something which would correspond to a nice polynomial in my variables would be a polynomial in the xi where maybe one part is multiplied by at most the power yi to the power 1. And so we have such things. So let me write this down. So for instance, here we are looking at, I've thrown at you these big power series polynomials, which you cannot really see, but let's just look here. So we have some monomial in the Siegel function. So this is again Ci, so the sum of them is 13. So the simpler ones. So in this case, we have this kind of trivial factor, which is just a monomial in the Siegel functions, multiplied by, in the denominator, we have this f at x2i. yi, numerator, we have the same f, and then the g. And the f and g are written down here, which are some big polynomials, but they are polynomials, not rational functions in these things. So and then we have the same, if we look, where is it? Where am I? It's difficult to handle this. Anyway, if we now have here Ci and C2i, then, okay, if we take the sum, it's just a polynomial, actually rather a simple one. And so it's always like this, the variable t is replaced by x, the variable y is replaced by y or y2i or whatever. And if I take their product, it's this. And there's again the surprising fact that the denominator is the same. Okay, and in fact, I should maybe mention that I did not, in these formulas, I don't have these other functions which come from the twisting. You can write also formula for the ones with the twisting. The non-trivial one is the bi, whatever, which corresponds to the Vafa-Witten class multiplied by the line bundle. And in that case, you find that if there are two different ways of writing it. In one way, the function is one gets the g. In the other case, one gets the f. So they also appear from somewhere else. And so anyway, you see here these complicated polynomials, but the nice thing is that they are just polynomials. And then in terms of these, you have just very simple rational functions. And then the other ones, we get these. So we have the E from before, we have again, and then we have again, if we take, so the complication is always how far, so Ci, C3i, and the corresponding complement, we have D divided by E, multiplied by something simple. And for, if I take the sum, it's C divided by E, where you can see the C and the D there. And I have C8i, Ci is 8i, and the corresponding complement on the other side, it's B divided by the same C. And if I take the product, it's the C for different things. They are kind of, you can see that they are kind of conjugated under the numerator, the denominator are conjugated under this hyperelliptic involution. Anyway, so these are these examples. So what is a little bit striking here, and what hopefully will eventually serve to determine all of them, is that you have all these different universal functions, and they share many terms, and so one has to see why. Anyway, in this, so it's not completely obvious, but this, if you kind of work out when you run through these indices, you get all of them. And so this means we have determined with this all the vertical Vafa-Witten invariants in rank 13, and thus also the vertical Euler. Maybe want to finish. I finally used my time precisely. So finish by saying something about the Vafa-Witten S2 conjecture. So I had this before on the blackboard. This was the S-duality, and then with Paul, we are apparently proving, but it's kind of clear that if one believes all the formulas I just showed you, and then and we define the Dij as the Cij at -1 over tau, then indeed the S2L conjectures will hold at least for all prime ranks smaller or equal to 13. For I think we will also get beyond the prime ranks by improving our arguments. And anyway, and the proof is based on the fact that now we have everything in terms of the Siegel functions, where we know how they act modularity, and then one has to we have these roots of unity all over the place, and one has to take care of them by means of Gauss sums. Okay, and there, yeah, I stop. Thank you.